Hello guys, and welcome to another calculus video. In this video we're going to be doing a competition math problem that asks us to estimate the integral from 0 to pi of e to the x dx. And obviously, since this is a competition math problem, we don't get any calculator, so we're going to do every single piece of long division, multiplication, and everything completely by hand, which I'm pretty sure I showed all of those on this video as well. So let's go ahead and jump right into the method for doing this. Now, I really like this class of problem because it tests a lot more than just your basic integration skills. It tests a lot of your intuition in terms of what's going to be a good or bad approximation and when you should truncate summations, stuff like that. So overall, I just really like this type of problem because it tests a lot of different critical thinking processes rather than just memorization of different integration techniques. So, this is a type of problem that's pretty common in math competitions. In general, you're going to have a limited amount of time, no calculator, no given values, and you have to estimate an integral as accurately as possible with a decimal representation. So that means we're going to be doing a lot of long division and math by hand, a lot of, multiplication and stuff, and we want to try to minimize the number of operations that we have to do while maximizing the amount of accuracy that we have in a very limited amount of time. So this is how I would attempt this problem. This was in a set of 4 problems that you would all attempt at the same time, but this is just how I would take on this one. So we have the integral from 0 to pi of e to the x dx. So we're going to set the integrand equal to u. We actually will find that dx is then going to be equal to 1 over u natural log of u du, which means that we just have the integral from e to the pi of 1 over ln u du. Now, the first thing to notice here is that e to the pi is extremely large, which means that we can start using asymptotic approximations for functions, because we're at the point where e to the pi is really like, I mean, it's a ridiculously large number. So we're going to be definitely using those asymptotic approximations. So we only need to consider the contribution for large numbers, and we can ignore most of the contribution for smaller numbers. So what this means is that actually we're going to be using the logarithmic integral function here. So this is going to be equal to the logarithmic integral of e to the pi minus the logarithmic integral of e. And again, since this has such a minor contribution, we only really need to focus on the magnitude of li e to the pi. Again, the logarithmic integral is just the integral of 1 over ln u du. So we're going to be using the fact that li of x equals the principal value of the integral from 0 to x of 1 over ln t dt, which is approximately equal to x over ln x as we get to larger numbers. This should actually probably have just one squiggly line because that means it approaches this value as x grows large. So this can be pretty easily derived just using IBP. So I have this over here. I'm just starting from e right here rather than from 0 because again we can ignore that contribution from smaller numbers. So when we integrate this, we're going to get x over ln x plus this separate residual integral here. But notice that in this integral we have 1 over ln t squared, which means on the order of e to the pi, this is e to the pi, or sorry, e to the pi less than the rest of the contribution, which since e to the pi is already a pretty large number, it's around like 30, we can pretty much ignore this and still get a relatively good approximation. We're also going to ignore the contribution from e right here. So we're just going to be using this approximation. Now you can go ahead and do integration by parts on this again, and you can get a much better approximation, but that does take a lot more time in terms of actually evaluating our integrals. So we're just going to be using the fact that li of x is approximately equal to x over ln x, and we're assuming that the contribution of this is going to be negligible for large x. So then we know that our I is approximately equal to li e to the pi, or e to the pi over e to the pi. So first, we have to calculate e to the pi, and the way I usually calculate stuff like this is I just memorize the values of ln2 and ln10, or if I back when I didn't have them memorized, what I would actually do was just go ahead and derive those first because it makes it a little bit easier, because then I can just separate this exponent into ln10 and ln2 plus some other residual term. And now I only have to calculate 20 times e to this number, and calculating e to this number, 0.145, is going to be a lot easier because I can truncate this series after just a couple terms because the terms will start to get smaller and smaller and smaller. So here e to the 0.145 is 1 plus 0.145 over 1 plus 0.145 squared over 2 plus 0.14145 cubed over 6. So I just went ahead and truncated after the next term. So what I did was 1 plus 0.145 plus 0.001. I got this just from multiplying 145 times 145 and then dividing this term by 2 right here. And also, if we were to multiply it by 0.15 again to get this term, notice that when we divide this by 6, this term is just negligible. I mean, it's like the fourth, it's like 10 to the negative fourth or something, and we're not really worried about terms that small. Again, if you wanted to get a more accurate approximation, you can truncate the series later, so you could include this term and maybe the next term as well. But I was trying to do this in as little time as possible so that it would be similar to the competition. So I added these together and then I multiplied by 20 to get that e to the pi is approximately equal to 23.12. And again, we want our value of I, which is e to the 23.12 over 23.12. And luckily for us, e to the 23.12 is really, really close to 10 to the 10 because of this nice little term right here. 23.12, remember we talked about ln 10 was 23.03. So I just used 10 times 23.03, and then we just have this, or 2.303, sorry, plus this residual term of e to the 0.09. And for e to the 0.09, I just used 1 plus x and truncated the series after that. So we know that e to the 23.12 is 10 to the 10 times e to the 0.09, or 10 to the 10 times 1.09 over 23.12. Then I went ahead and did some long division right here, and I got 0.0471 for this long division, and then I just put it in scientific notation. So I got that our integral I is approximately equal to 4.71 times 10 to the 8. Now I was hoping for an error of about 5% after doing all this math. I believe this took me about 10 to 13 minutes to figure everything out here. So this was the best I could probably do. I probably could have gotten a better approximation by truncating the series less, by using 3.142 instead of 3.14 maybe for pi. I'm not sure which value of pi I used. And maybe also by using that next term in the approximation for Li of x. Again, I said it was x over ln x plus x over ln x squared is a more accurate approximation. So let's go ahead and see. Plugging this into Desmos, we get that the actual answer is 5.07 times 10 to the, that should say 10 to the 8, not 10 to the 10. Sorry, this is 10 to the 8. We were actually pretty close. I was pretty surprised that I was able to get a good approximation. Again, this should say 10 to the 10, or 10 to the 8. And so, again, when we're dealing with such large numbers, getting on the same order of magnitude already is a pretty good, I'd consider it a success just to get on the same order of magnitude. And we actually only got 7.1% error when we calculate the percent error on this. And so most of the error actually comes from the initial approximation that we made, where Li of x, because Li of x is 4.7% greater than x over ln x at x equals e to the pi. And obviously, as x grows larger, this error decreases. However, if we wanted to obtain a more accurate approximation, we could calculate this, which I mentioned before, that Li of x, this is a more accurate approximation of Li of x for smaller x. And this approximation has an error of just 0.4% at x equals e to the pi, which means 10 times less error. The only problem with this is in a competition situation, we wouldn't really have a lot of time to be able to calculate, e to the 2 pi and e to the pi, and then go ahead and divide them. It probably would have been a good idea if we had maybe like 20 or 25 minutes to do this, but I was, again, trying to get it done in very little time. So this method would probably not be effective, again, with limited time. So I hope you guys enjoyed the video. I really had a lot of fun making this. If you guys have any other ideas on how to gain a more accurate approximation of this integral by hand, please let me know because, I'm always interested in this sort of thing. I think doing math by hand with no calculator is a great, great exercise for your brain, not only just for, doing math methods, but just in general for figuring out better ways to do things. So anyway, if you enjoy this type of video, please let me know and I can continue making them. You can go ahead and join my Discord, which should be linked in the description. Yeah, thanks for watching. I'll see you next time.